welcome to part 3 of chapter 10. Today we're going to talk about electronegativity and bond polarity. So electronegativity is a topic that we've already talked about in class when we did periodic trends back earlier in the semester. And so now we're going to talk about it and use it to figure out if bonds are polar and then if molecules are polar. So that's kind of the overarching thing of today. So also you need to be really good at drawing Lewis structures. I know I keep saying that, but it's really important because if you don't draw the Lewis structure right, then you're not going to get whether or not the molecule is polar or not. So again, make sure you are practicing drawing your Lewis structures. So we can learn more about the chemistry of compounds by understanding how the electrons are shared in the bonds. So in these molecules, we know that electrons are being shared, but this doesn't mean that they're being shared equally, right? So, you know, if bonds are formed by identical atoms, then those electrons are being shared equally. They'll be shared like right in the middle. So this would be like, you know, if a hydrogen bonds to another hydrogen, since those are the same atom, they have the same electronegativity, which means that these electrons are going to be shared equally. You can think of the electrons as sitting right in the middle between the two atoms. But if we have bonds formed between different atoms, then the electrons are not going to be shared equally. So this would be something like if you want to think hydrogen and fluorine. So if we have hydrogen and fluorine, fluorine is super electronegative. So if we look at this, fluorine has an electronegativity value of 4.0, hydrogen is 2.1. So since fluorine is way more electronegative than hydrogen, it's kind of an electron hog. It pulls the electrons towards the fluorine. And so rather than the electrons sitting directly between the hydrogen and the fluorine, the electrons will actually sit closer to the fluorine than they will to the hydrogen because fluorine is more electronegative. So if we share, you know, if they're identical or, you know, similar in electronegativity, they'll share them equally. If there's a difference in electronegativity values, then they won't share them equally. And so this is the big kind of focus of today. So this is a reminder about what electronegativity is. Electronegativity is the relative ability of an atom to attract shared electrons. So this is the, you know, the ability of the atom to kind of pull the electrons in the bond closer to it versus the other atom. Electronegativity values are really high for nonmetals, and since we're doing all molecular, right, all covalent molecules, these are all going to be nonmetals anyway. Just as a heads up and a reminder, fluorine has the highest electronegativity value, 4.0. It's really high. You know, if you're thinking about periodic trends, so it's not, you know, it increases going to the to the right and up, which would kind of point to helium. But remember, the noble gases have an electronegativity value of 0. So fluorine is instead our most electronegative atom. You'll have access to these electronegativity values, but it's really helpful to just kind of remember general trends. So if you can remember that electronegativity increases going to the right and up, that will save you some time and you won't always have to pull out these values. But fluorine has the highest electronegativity value. It's really low for metals like cesium and francium. This is actually why metals make ionic compounds, right? Or one of the reasons they make ionic compounds. They have really low electronegativity values, and so the nonmetals essentially just pull the electrons right off of them. Again, increases as you go to the right on the periodic table, and it will decrease going down or, you know, increase going up. So here's our values. Again, we're mostly going to be working with the nonmetals over here in the yellow. If you'll recall, the ones in the green, those are metalloids. They'll sometimes do covalent bonding. But the ones in blue, those are all metals, and we're not going to be messing with those right now because we're just doing covalent compounds. So bonds can be described by the difference in the electronegativity between the bonding atoms. So we have two different types of bonds, two different types of covalent bonds. We have nonpolar covalent bonds in which the electrons are being shared equally, or at least mostly equally. And then we have polar covalent bonds in which they are being shared unequally. And the way that you're going to determine whether they're shared equally or unequally will be looking at those electronegativity values. If they have similar electronegativities, then they're going to be shared, excuse me, then they'll be shared equally. If they have really different electronegativity values, then they're going to be shared unequally. And we have some cutoffs. So if they're being shared equally, so if they're being shared equal or almost equal sharing of electrons, so this will be a difference of 0 or really close to 0. So here's our range. We're looking for a difference in electronegativity of 0 to 0.4. So if they're in this first one, if they're both nitrogen, then they have the same electronegativity, right? Each of those nitrogens has the same electronegativity value, so their difference is 0. So we didn't really need to go through the subtraction because we know that they're the same atom. And this would be what we call nonpolar because the electrons are not being shifted one way or the other. The electrons are going to sit right between those two nitrogen atoms. They're going to sit right in the middle. If we look at chlorine and bromine, chlorine has an electronegativity value of 3.0 and bromine has 2.8. This is an electronegativity difference of 0.2. This is very small. So even though it's not 0, it's really, close to 0. It's small, right? And it falls within this range. So this range here, anything that falls in there, we're going to call nonpolar. So they're being shared equally or almost equally. So again, this will also be nonpolar covalent. Okay, and so like I said, we figure that out by subtracting those values in this table here. So chlorine and bromine. If we have a large difference, a large electronegativity difference, so greater than 0.4, so this will be between 0.5 and 1.7, then we call this polar. So now the electrons are not being shared equally. Those electrons are not going to sit right between the two atoms, right in the middle. The electrons are going to be shifted closer to one atom or the other. And so they'll always be shifted toward the more electronegative atom. So here, oxygen and chlorine, oxygen has an electronegativity of 3.5 and chlorine has 3.0. This difference is 0.5, so this falls, even though it's kind of at the lower end of this range, right? This is classified as polar. And so the electrons are going to sit closer to the oxygen because it's more electronegative than the chlorine. Similarly, if we look at chlorine and carbon, chlorine has 3.0, carbon is 2.5, so this is a difference of 0.5, which again falls in this range. So the electrons won't be shared equally. They'll be sitting closer to the chlorine because it's more electronegative. Nitrogen to hydrogen has an even larger electronegativity difference, 0.9. So this is definitely polar, right? Falls kind of right in the middle of our range. And so again, the electrons, rather than being shared equally, will sit closer to the nitrogen than they will to the hydrogen. So this is for polar covalent bonds. Okay, so the one on the picture on the left, this is nonpolar, right? If we look, the two hydrogens, they have the same electronegativity value. Those electrons are going to sit right in the middle. They're going to be shared equally. So this is nonpolar. And so that's what the picture is showing here. These electrons are sitting directly between the two hydrogen atoms, not closer to one or the other. Here on the right, we have hydrogen and chlorine. Hydrogen has an electronegativity value of 2.1. Chlorine has an electronegativity value of 3.0. So this difference is 0.9, which is quite large. And so this is polar. Okay, so the electrons will not be shared equally. I know it's a little bit hard to tell, but these electrons here are actually sitting closer to the chlorine than they are to the hydrogen because chlorine is more electronegative than hydrogen is. And if you see these little signs here, these are a new symbol for us. These are the Greek letter delta. So not the capital delta. We talked about the capital letter delta way back earlier in the semester. That was a triangle, right? Like change in temperature, right? The capital letter delta means change. This is the lowercase Greek letter delta, and this means partial, okay? So like partial positive and partial negative. So the reason that chlorine gets a partial negative is because these electrons are sitting slightly closer to chlorine than they are to hydrogen, which means that chlorine kind of acts like it gained electrons. It didn't really, right? That's why we're not putting a negative charge. It didn't gain an electron and transfer it and all of that. But since the electrons are sitting closer to the chlorine, it looks like it kind of gained electrons. So that's why it gets a partial negative. Since chlorine kind of gained electrons, hydrogen feels like it kind of lost electrons, which is why we're putting this partial positive on hydrogen. Again, it didn't really lose them. They're still being shared in that bond, but since they're sitting closer to chlorine than they are to hydrogen, hydrogen feels like it got, kind of left out. And so the electrons, right, it looks like it kind of lost some electrons, and chlorine kind of gained some electrons. So that's where you'll see those. The partial minus, just so you know, will always go on the more electronegative atom. So you can just figure out which one is more electronegative, put the partial minus on that one, and then this one will go on the one that is less electronegative. So bonds become more polar as the difference in electronegativity increases. A polar covalent bond, it has a separation of charge, is called a dipole. So if you see this word, this dipole, that's just telling you it's a polar bond, essentially. And again, the positive and negative ends are represented by the Greek letter delta, right, that lowercase delta, with a positive or negative charge. So we can write partial plus or partial minus. Okay, and they kind of, the way that we write them is we kind of just write them as like an open 8, or you can kind of write them like this. Right, so that would be how you write them, like on your paper. And so then once we have figured out, the partial plus and the partial minus, we will assign these arrows. And so the arrows are normally what we talk about. If we say the word dipole, we're usually talking about these arrows. But let's look at the first one. So carbon and oxygen. If we look at their electronegativity values, carbon has a value of 2.5, oxygen has a value of 3.5. Okay, so the partial minus, right, is going on the oxygen because it is more electronegative. So the partial plus went on carbon because it's more, electropositive or less electronegative. And so the way that we draw these arrows is we're always going to put a plus at the positive one and then finish our arrow toward the negative one. So the arrow is always going to point at the more electronegative atom. So let's do the next one. So nitrogen and oxygen. I know it's already got the partial, positives and minuses assigned, but let's just go through the motions. So this has 3.0. Oxygen is 3.5. So this is kind of at the lower end of our, polar range, but it's still polar. And again, we put the partial minus on the more electronegative one, and so the other one gets the partial positive. The way that we draw the arrow, we put the positive, or the plus sign at the positive one, and then finish our arrow toward the negative one. Same thing over on the next one. Chlorine is 3.0, fluorine is 4.0, so the delta minus went on the more negative one, more electronegative. And so then we put our plus sign at the more electropositive or less electronegative, and then we finish our arrow toward the more electronegative. That is how we draw the dipoles. So you only do these for polar bonds. If it's a non-polar bond, we can't draw these arrows. So only for polar bonds. And then again, these arrows are called a dipole. So here's kind of a summary slide. If you have an electronegativity difference of 0 to 0.4, we call that nonpolar, and the electrons are shared equally. If you have a difference of 0.5, this has 1.8. This range kind of varies, just so you know. Pretty much if it's two nonmetals and it's more than 0.5, then they fall in this polar covalent. Okay, so polar, they're being shared unequally, and that's where we get this partial minus, partial positive, right? And again, we can draw our dipole arrows, put a plus at the positive one, and then finish our arrow toward the negative one. And then if it's greater than 1.9, sometimes you'll see this as 1.8, sometimes you'll see it as 2.0. It kind of changes. But again, you could look and see if it's, if it's a metal and a non-metal. That would be an easier way, I think, to recognize that it's ionic, and the electrons are being transferred. So they're not being shared anymore like in the other two. They're being transferred. So that's why we see this complete positive charge and this complete negative charge, because one of the atoms has actually gone through and lost electrons. The other one has gone through and gained electrons. Rather than in the polar covalent, we're seeing these partial positive, partial negatives, because the electrons are being shifted in the bond rather than being actually transferred from one to the next. So here is a summary slide, right? A bunch of examples. So, you got two nonpolar, and then two polar and two ionic. So you can, check those out, just examples for you to look at. So go ahead and pause here and try and complete this table. Figure out, based on their electronegativity values, is this, polar covalent? Is it non-polar covalent? Is it ionic? What are we doing here, right? So try and figure out, based on their differences in electronegativities and or based on whether they're metals or non-metals, figure out what type of bond you've got going on. All right, so if we look at their differences in electronegativity, silicon and sulfur, those are both, well, silicon's a metalloid, but usually it'll act like nonmetals in bonding. So we'll look at their difference in electronegativity. They have an electronegativity difference of 0.7. So this would be classified as polar covalent. The electrons are being shared, but they're not being shared equally because they have a fairly large difference in electronegativity. Cesium and chlorine, if you look, cesium is a metal. Chlorine is a nonmetal. So even just based on that, we would recognize that as ionic. But you could go through the motions and calculate their electronegativity difference. It's really big, right? Really, really big. So that tells you that it's ionic. The electrons are being completely transferred. And then silicon versus phosphorus has a very small difference in electronegativity. So the electrons, even though they're not being shared completely equally, it's like pretty equal. So we classify this as nonpolar covalent. So always make sure you're looking at the ranges. Remember, 0 to 0.4, we're going to say is nonpolar. And then 0.5 to 1.8, we're going to say is polar. And anything over that, you can classify, 1.8. Anything over that, you can classify as ionic. So go ahead and find your lecture worksheet and do problem 14. This will get you some practice trying to figure out whether it is polar, nonpolar, or ionic. So do that first before you continue the rest of the lecture, because we're going to use this figuring out whether bonds are polar or nonpolar to figure out whether molecules are polar or nonpolar. So you need to do that work first. So pause here and then come back. All right, so now we've figured out how to determine whether bonds are polar or nonpolar. So now we're going to use that to figure out whether molecules are polar or nonpolar. So in a nonpolar molecule, we have two different kind of ways that something can be nonpolar. One of the ways is that all of the bonds are nonpolar themselves. So if we look in, like in this one, in hydrogen, right? Hydrogen to hydrogen, they have the same electronegativity value. Their difference would be 0.0. That would be nonpolar. So that bond is nonpolar. That's the only bond in the molecule. So that is nonpolar molecule. Same thing with the chlorine, right? That is, and it should show all of these dots here, right? All of these lone pairs. But since there's two chlorines bonded to each other, again, they have the same electronegativity values. So if you subtract, chlorine minus chlorine, you're going to get 0. So those electrons are being shared equally as well. And then we can look at, carbon to hydrogen. Carbon has an electronegativity value of 2.5, and hydrogen has an electronegativity value of 2.1. So that means all of these bonds are 0.4. So it's kind of the upper end of our nonpolar range, but we still classify these as nonpolar. They do fall in that range. So this would be, these are examples of when all of these bonds are nonpolar, right? So molecules, like if you look right here, molecules such as H2, Cl2, and CH4 are nonpolar because they contain only nonpolar bonds. So they can't be polar because all of the bonds are nonpolar. The other way that something can be nonpolar is when we have polar bonds, but the molecule is symmetrical. So these polar bonds will actually end up canceling each other out. So let's look at carbon dioxide here. So again, they should have all of these, okay? But if we go through and we look at, carbon and oxygen, and we determine their electronegativity values, carbon has an electronegativity value of 2.5 for carbon, and oxygen has an electronegativity value of 3.5. So when we subtract those, we get an electronegativity difference of 1.0. These are definitely polar bonds. So we can go through and assign our partial positives and our partial negatives. Since oxygen is more electronegative than carbon, we will put our delta minus on oxygen and our delta positive on carbon. Same thing over here. Delta minus on oxygen and delta positive on carbon. So we'll draw two different dipoles, one for each of these bonds. So here we put a plus on carbon, finish it toward the more electronegative atom. Put the plus on carbon, finish the arrow toward the more electronegative atom. So we have two different dipoles. Okay, you have to draw an arrow for every single bond in the molecule. Double bonds still kind of count as one bond. They count, it's kind of like before when we were looking at areas of electron density, right? And we counted that as one. So a double bond just kind of counts as one bond here. But if you'll look, those arrows are going in exactly opposite directions. They are equal and opposite. So since they are equal and opposite, they are going to cancel out. Okay? And since they cancel out, because they are exactly equal and exactly opposite, then carbon dioxide is a nonpolar molecule. Okay, so that would be something that you need to look out for. Here, if we look, this is carbon tetrachloride, the next one on the right. And I'm going to draw the Lewis structure for that just because it's a little bit easier to see rather than this three-dimensional structure that they've drawn. So this is carbon tetrachloride. And so then we can go through and figure out, okay, are these bonds polar or nonpolar? Chlorine has an electronegativity value of 3.0, and carbon has an electronegativity value of 2.5. So if we subtract those, we get an electronegativity difference of 0.5. So this is these are polar bonds, because they fall within that range. So then we can go through and assign all of our partial negatives and partial positives. So chlorine will be the one that gets the partial negative, and because it's more electronegative, and carbon will be the one that gets the partial positive. So we go partial negative, partial negative, partial negative, partial negative, and then carbon will get the partial positive. This is going to get a little crowded. And then we're going to draw arrows for every single bond in this molecule. And if you look, since carbon is the one that's positive for all of these bonds, and it's always the chlorine that's negative, all of these are going to go out. All right, so there you go. I know it's a little bit hard to see. So if we look at the chlorine on the left and the chlorine on the right, like these arrows, so this arrow and this arrow, they are going exactly opposite directions. One of the arrows is going exactly left and the other one is going exactly right. So those are going to cancel out. And then if we look at the chlorine on the top and bottom, we have one arrow going exactly up, the other one going exactly down, right? So they are, again, equal and opposite. So those two arrows will cancel out. So the arrows going left and right cancel. The arrows going up and down cancel. So we have no leftover arrows. There's no arrows that don't get canceled. Therefore, this molecule is nonpolar. Okay, again, it's kind of hard to see it when it's drawn like this in this three-dimensional shape, and I haven't taught you how to draw it like that anyway. But if you draw it, in this, like we would normally draw a Lewis structure, it's really easy to see that the left and the right cancel and the top and the bottom cancel. And so this is a nonpolar molecule. So like I said, two different ways that it can be nonpolar. The first way is if all of the bonds are nonpolar bonds, then we don't draw any arrows, so there's nothing to worry about. If we have polar bonds, then we have to figure out, do the arrows cancel? And so if all of the arrows directly cancel out, then we have a nonpolar molecule. Okay, so you need to be able to draw these arrows, and again, it goes back to drawing Lewis structures. If we have a polar molecule, this is when the dipoles don't all cancel. Okay, so if they don't all cancel out, then there's going to be an overall polarity to the molecule. This will happen if we have like asymmetrical molecules, and a lot of times this will be when we have lone pairs on the central atom. So if you see lone pairs, it's probably going to be a polar molecule, but you still need to go through and check. But the big thing here is that to be polar, our bonds do not cancel each other out. So let's try this out. If we look at HCl, HCl is linear, right? And our bond, if we look, chlorine has an electronegativity value of 3.0. Whoa. And hydrogen has an electronegativity value of 2.1. So if we subtract those, we get a difference of 0.9. This is quite polar. So then we would go through and we would put our partial minus on chlorine because it's our more electronegative atom. And then we would put the partial positive on hydrogen because it's more electropositive. And then, again, we put the plus by the positive one, finish the arrow toward the negative one. So this is a polar bond, okay? And there's nothing for it to cancel out with. Since it's the only bond in the molecule, we can't draw any more arrows. So there's no arrow going in the opposite direction to cancel it out. So this is a polar molecule, okay? Because it's got a polar bond. So that's one way. So if we have, if there's only one bond and that bond is polar, then the molecule is polar. If we look at water, and I've talked a lot about the right way to draw water, and this is why. So yay, we finally got to it. If we look at the right way to draw water, it has the lone pairs next to each other, right? Again, we always want to do, like I said, put them on the sides of the box like that. And so these bonds to hydrogen end up being kind of next to each other. So this is a bent molecule. And if we go through and we figure out, their electronegativity values, oxygen is 3.5 and hydrogen is 2.1. So we subtract those. We get a very large difference in electronegativity, right? This is super polar, these bonds. So again, we're going to put the partial negative on oxygen, partial positives on hydrogen, and we're going to draw the arrows. So put a plus sign at the positive one, finish the arrow toward the negative one for both of the bonds. And so, if we're looking at this, these arrows do not cancel out. Even though, they're both oxygen and hydrogen, they are not going in exactly opposite directions. One is going up and to the right, the other one's going up and to the left. So these are not exactly opposite. These bonds do not cancel. Okay, so since the bonds do not cancel out, this molecule is polar. Okay, and again, a lot of times this will happen when we draw lone pairs. So here is why I'm picky about the way that you should draw water. If you had drawn it like this, right? Which is why, the way I said bad, don't draw that, right? This would be our partial negative, partial positives, okay? And then we would draw our arrows. Put a plus sign at the positive one, finish the arrow toward the negative one, put a plus sign at the positive one, finish the arrow toward the negative one. And now look, those arrows would be going exactly opposite directions. And so if you drew water like this with those split, right, where you put the lone pairs on the top and the bottom, if you drew water like this would make you think that water is non-polar, right? And I know that doesn't sound like a really big deal, but pretty much all of the properties of water, and water is really abundant, right? Water is everywhere. Pretty much all the properties of water, and why water is so cool is because water is polar. And so we know this is not true. This is not true at all. And so make sure you always, always, always draw water correctly. Otherwise, if you draw it wrong, you're going to think water is non-polar, which is a big, big lie. So that's why I'm really picky about the water thing. Here's another one, NH3. So I'm going to draw it down here a different way because it's a little bit hard to see up there the way it's drawn. So if we do this, okay, so this is trigonal pyramidal shape. And so if we go through and we figure out, are the bonds positive? Nitrogen has a value of 3.0. Hydrogen has a value of 2.1. And we subtract them, we get 0.9. So these are polar bonds. So we have to draw our dipoles. We're going to put our partial negative on nitrogen because it's our more electronegative atom. And then all the partial positives on all the hydrogens. Okay. And then we can go through and draw our arrows. So for each one, the positive is going to be at the hydrogen. We're going to finish our arrow toward the nitrogen. So in looking at this, right, ask yourself, is this polar or non-polar? So the first question I usually ask is, do some of the arrows cancel? And your answer should be, yeah, there's one going exactly right and there's one going exactly left. Those two arrows appear to cancel. But do we see the arrow on the bottom? The arrow on the bottom has nothing to cancel out with, right? So we're going to have a leftover dipole, right? This one cancels with this one, and so they're going to be gone, but the leftover arrow going straight up is going to cause this entire molecule to be polar. So this is polar because not all of the dipoles cancel. So if some of them cancel, that's okay. It might still be polar. So as long as you have one arrow left over, it's polar. Here's kind of an unusual example. This one's a little bit tricky. CH3F. So if we drew that, all right, so now we have a couple different things to look at. So we have 3 carbon-hydrogen bonds. So carbon has an electronegativity value of 2.5. Hydrogen has an electronegativity value of 2.1. That difference is 0.4. The carbon-hydrogen bonds are non-polar. We do not draw arrows for non-polar bonds, so you won't draw any arrows for the carbon-hydrogen bonds. So then we look at the carbon-fluorine bond. Carbon, again, electronegativity value of 2.5, and fluorine has an electronegativity value of 4.0, super polar, right? Or super electronegative. So this difference, I kind of wrote them in a different order. This difference would be 1.5. That's very polar. So this bond, this carbon-fluorine bond, we would need to draw an arrow for. So we put our partial negative on the more electronegative atom, our partial positive on the less electronegative atom, and again, we put a plus sign by the positive one, finish the arrow toward the negative one. So looking at this, we only drew one dipole. We only drew one arrow for this molecule. And so there's nothing for that arrow to cancel out with. So since there's nothing for it to cancel out with, we have a leftover dipole, leftover arrow. So this is a polar molecule. So again, drawing these, right, you need to be able to draw the Lewis structure correctly in order to be able to figure out whether the molecule is polar or non-polar, because it all has to do with the shape. Okay, that one is a little bit tricky though. This is probably one of the tougher ones. So let's try this. Again, to figure out if something is polar or nonpolar, you're first going to figure out, are the bonds themselves polar or nonpolar, right? If all of the bonds are nonpolar, then the molecule is nonpolar. But if the bonds, right, if there are polar bonds, then we need to go see if the dipoles cancel out or if there's going to be a leftover polarity. So let's try this. Determine if the molecule OF2 is polar or nonpolar. So thinking about our Hunk rule, oxygen can make 2 bonds and fluorine is a halogen, so it can only make 1 bond. So we're going to put our oxygen in the middle. And again, remember, whenever I told you when you put oxygen in the middle, be careful because those lone pairs are going to end up next to each other. So I'm going to put 1 fluorine here, 1 fluorine there. If you put the fluorines across from each other, you're going to end up like, you know, I told you the wrong way of drawing water. So just be careful. So then we figure out how many electrons we have to use. So our electrons, we have oxygen plus 2 fluorines. So 6 plus 2 times 7 will get us 20. So we're going to use 2, 4, making those bonds. So we're going to subtract out 4. We got 16 left. So we say, okay, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. And everything has an octet, so we are good to go. Then we need to figure out, are these bonds polar or nonpolar? Because again, remember, if all of the bonds are polar, if all of the bonds are nonpolar, then the molecule is nonpolar. So that would be an easy way to just kind of be done. So let's see. So we have oxygen, and oxygen has an electronegativity value of 3.5. We have fluorine, and that has an electronegativity value of 4.0. Our difference here is 0.5. So these are polar bonds. So we need to go through and draw the dipoles. So we're going to put our partial negatives on fluorine because it's the more electronegative atom, partial positive on oxygen. And then we're going to draw our arrows. Remember, plus of the positive, finish it toward the negative one. Plus of the positive, finish the arrow toward the negative one. And then we need to see, do our arrows cancel out? Do they go in exactly opposite directions? And so our answer here is no. One of them is going to the left. The other one is going straight down. Our dipoles do not cancel. So since our dipoles do not cancel, this molecule is polar. Okay, so this will take some practice. But again, the better you are at drawing Lewis structures, the better you're going to be able to figure out whether things are, polar or nonpolar. So you need to go through all the steps, make sure you're practicing your Lewis structures, all that good stuff. So you have lecture worksheet problem 15 to help you practice with that. It's going to have you figure out whether, your compound or your molecule is is molecular or covalent, right? Or is it ionic? And if it's covalent, if it's molecular, then you're going to draw the Lewis structure and figure out, is it polar or non-polar? Okay, so this will be some good practice for you.